Hello friends, I welcome you all to this session on power plant engineering. So from today I'll be starting a new topic, that is analysis of steam cycle, and this will be having several parts. This is a very big topic, and so let us start it. So first let us see that how a steam power plant works. Basically the major components, and then we'll be gradually moving from this point to the Rankine cycle. So, steam power plant continuously converts the energy stored in the coal or fossil fuel, that is coal or it can be oil or gas as well, into shaft work and ultimately into electricity. So, if I write that fossil fuel, the energy of fossil fuel is basically getting converted into shaft work, and this ultimately gets converted into electricity. So, in any power plant in general, you should have one furnace. Okay, now what we do in furnace, we supply air to it and fuel to it. Let's say m dot f is the mass flow rate of fuel and m dot a is the mass flow rate of air. Here inside the burning will take place and heat will be generated. Now this heat, let's say Q1, is transferred to boiler. What are boilers? Boilers are basically steam generators. Okay, so the working fluid in case of steam power plant is water. So water gets converted into steam, then again that steam is being converted into water, and this forms a cycle, and in between work is being generated. So here the heat Q1 is transferred to the boiler, due to which immense amount of steam will be generated at high pressure. This high pressure steam is then transferred to turbine where the shaft work is produced. Where the shaft work is produced, and this is basically transferred to a generator which produces electricity. Whereas from turbine, the steam which is coming out is of very low pressure, so it is transferred to uh, condenser where the condensation of steam takes place via external sources, with the help of external sources like river water or sea water. And in general what we do is there is a cooling tower. So there is a cooling tower, you might have seen, and that energy is being discharged there and ultimately to the atmosphere. And then this condensed low pressure water is transferred to a pump which increases the pressure of the water, exactly matches to the boiler, and then that water is being fed to the boiler. Here if you look, here water is in vapor superheated state. Here again the water is there in this particular case, that means in generator case water is there, uh, sorry, after turbine water is in steam state, but it is of low pressure, very low pressure. And then here this water is in liquid state, and here also, and the pressure is low. Here also it is in liquid state, but the pressure is high. So in this way, if you look, And what is happening? And here we have to supply some work. This is called as pump work to to convert low pressure water into high pressure water. So if you look this thing closely, then you are doing what? You are creating a cycle. And what type of cycle is this? This is basically a closed cycle. A cycle is always closed. But this is what we call as a Rankine cycle happens here. We'll talk about Rankine cycle in detail in the next lecture. Right now, if I apply the first law of thermodynamics, which says that in a cycle, the net heat transfer is equal to the net work done. So here, the heat transfers to this particular cycle, if you look, then what are they? The heat transfer first Q1 to the cycle, that is positive, and then Q2 from the cycle, which is negative. And that will be equal to the shaft work, or sorry, net work. What is the net work? Work done by the system is positive, you know. So this is positive, and work done on the system is negative, and this is the work done on the system. So this is minus W dot P. So if you slightly solve this, so this will become Q1 minus Q2, and that is equal to W dot shaft minus W dot pump. In fact, these are rates, so you should be writing rates as well. Now, for any cycle, the efficiency matters. So how to evaluate efficiency? It is the net work done in the cycle, or from the cycle, to that of the energy input in the form of heat. So this is net work done rate, and this is net heat transfer rate. So this eta will then be equal to W dot shaft minus W dot P divided by Q1. Now this can also be written as W dot shaft minus W dot P is nothing but Q dot 1 minus Q dot 2 divided by Q1 dot. So this can also be written as 1 minus Q2 dot by Q1 dot. So in this way, efficiency can be written in terms of heat transfer. So now you know that in general how energy transfer, energy interaction takes place in case of boiler, in case of a power plant, steam turbine, steam power plant, and what are the basic building blocks of a steam power plant. In the next lecture, what we'll be doing is we will be learning about starting from here itself and learning about the Rankine cycle. So in this lecture, till this point only, thank you very much.